A multi-rate signal refers to a data set where you have different variables that are sampled at different sampling rates. So imagine you're measuring from 3 sensors, 3 different measurement devices. They're all being recorded at the same time, so simultaneous measurements of the same system. Maybe one is video, one is audio, and one is, I don't know, something else. Let's say a force plate that someone is standing on. And these are all measuring the same system in different ways, but they have different data sampling rates because they are coming from different acquisition devices or different technologies. So the question is, what do you do with such a multi-rate signal? The answer is actually pretty straightforward. You have 2 options. One, you can upsample everything to the signal that has the highest sampling rate, so that would be the blue diamonds in this case. Or 2, you can downsample everything to the white circles or the signal with the lowest sampling rate. Neither one is necessarily better or worse than the other. However, I would generally recommend to upsample as opposed to downsampling. And the reason is that if you downsample, you are losing real information, you're losing valid information. So if you would downsample the blue diamonds and the green triangles to the sampling rate of the white dots, then you're losing information from this signal and you're losing information from this signal. On the other hand, if you would upsample both of these 2 signals to the sampling rate of the blue diamonds, then you're not actually losing any signal anywhere. You're not losing information. You are making some assumptions, for example, about smoothness going from this point to this point, but there's no loss of information. All right, so I'll switch to MATLAB now, and I will show you an example of dealing with multi-rate signals. So here I'm going to generate 3 signals. It's hard-coded. I hard-coded parts of the script to be 3. So if you would like to modify this code to add additional signals, then you might need to be careful about changing some of these variables here. Okay, so I'm specifying that the first signal is 10 hertz, the second signal is 40 hertz, so that's a nice ratio of 1 to 4. But the third signal was measured at 83 hertz, so that makes things a little bit more complicated, or at least it's not possible to upsample just by multiplying these by some integer value. Okay, so then here I create the signals. This is random numbers that are normally distributed, so these numbers will randomly appear either on the left of 0 or the right of 0. Then I take the sign, so basically this means I'm going to get a time series of random -1s and +1s, and then I take the cumulative sum, which is the discrete integer, and that just gives kind of like a choppy Brownian motion like time series. Okay, and then the thing is that each of these variables needs its own time vector because I'm sampling them at different rates. So, and this looks a little bit confusing initially, that I'm saying that the sampling rate is the number of time points to generate, but essentially this just means that there's going to be 1 second of data. So 10 samples at a sampling rate of 10 hertz corresponds to 1 second, and 40 samples at 40 hertz is 1 second, and 83 samples at 83 hertz is 1 second. So if you want to simulate the data for longer, you could do, for example, 5 times the sampling rate, and then this would give you 5 seconds of data. Of course, you would also need to modify this here. Okay, so let me get rid of this. And then here I make the plot. All right, so here you see what this data set looks like. So the red line is for the 83 hertz signal, the blue line is for the 40 hertz signal, and the black line is for the 10 hertz signal. Okay, so now in this next cell of code, I upsample to the fastest frequency. And actually, this isn't doing the upsampling yet. This is just figuring out which is the highest frequency rate in this data set. So I'm getting out all of the sampling rates. This is in a cell, so I'm using the MATLAB function cell to mat to convert this cell into a matrix. And then I simply find the maximum value. So that's going to give me these 2 outputs, which is the new sampling rate. So this is the value of the fastest sampling rate. And this switches fastest variable that tells me that it's the third data set in this cell array that is the fastest. Okay, so actually the rest of the code in this video is the same as the code that you saw in the video on upsampling. So I figure out what is the new number of time points, I generate a new time vector. Now, unlike up here when I generated the signal, I needed to create a separate cell for each time vector. But now I'm upsampling all the data streams to the same sampling rate, so I only need one common time vector. Here I'm using the MATLAB gridded interpolant function to do the interpolation, which is going to give me the upsampled signal, and that I do here. And again, this is exactly the same procedure that I applied in the previous video on upsampling. All right, and then I'm going to plot all these signals, and I plot them in figure 2, so we will be able to compare it with the original data in figure 1. Oops, I have to actually run this code first. So run that cell, run that cell, run that cell. Okay, so now it's interesting to compare back and forth between these two. You can see that the red line is the same, no surprise, that's 83 Hertz in both cases. And the blue and the black lines are upsampled and a bit interpolated. So you see they are a little bit different here because there is this spline interpolation. So they get a bit smoother, and they also get interpolated out here.